Okay, hello everyone. So in this lesson, we'll be learning about X-rays. We've already covered photoelectric effect. Okay, so describe the purpose of the following features of a simple X-ray tube. That is the filament, the target, the high voltage supply, the evacuated tube, and the means of cooling the target. And X-ray photons can be produced when electrons that have been accelerated to high speeds interact with a target. Okay, a simple X-ray tube would be something like this, right? It consists of a battery that heats up the filament, and it consists of a high tension power supply in the region of kilovolts. So this is your filament. So when this switch is closed, current flows through this filament. It heats up the filament and produces a cloud of electrons. So to produce X-ray, you close this switch, the high tension switch, which makes this target positive, this filament negative. So the electrons that are negatively charged particles will accelerate towards the target that is positively charged. So in the process, when the electrons hit the target, they will lose kinetic energy. In the process where they lose energy, they will emit energy in the form of photons. So a simple X-ray tube consists of a filament, right? Two power supply, one power supply that heats up the filament, and the other power supply that is used to accelerate electrons to a high potential. So this whole thing must be kept in vacuum. And the reason why it's kept in vacuum is so that electrons do not collide with air particles and lose kinetic energy. We want the electrons to collide with the target, not with anything else. Okay, this here, the target, right, is made up of copper. The reason why it's made of copper is so that it's a good heat conductor. Because a lot of energy, right, when the electron hits the target, a lot of its energy will be converted to heat. So heat is of no use, right? What we want is X-ray. So to dissipate this heat, we need this to be made up of copper. So sometimes there is what you call as cooling fins. So if I have cooling fins, right, this is where you have cooling fins here. So the cooling fins is basically to cool down the target. Okay, so how is X-ray produced? So electrons here, the filament, right? These are the electrons. And this is the target. So the target is placed at a positive potential, a high positive potential. So the electrons that are negatively charged particles will see that the target is positive, so they will accelerate towards the target. And in this process, when they collide with the target, they will lose energy. So what is depicted here will be the electron that comes in, right? Depending on how close they approach the target atom. When they collide, right, they lose kinetic energy. And in the process where they lose energy, energy lost by the electrons will be converted to photons. So the closer they are to the target, the more energy that the electron loses. So the higher the energy of the photon emitted. So you find that there'll be a lot of photons being emitted. And these photons all will have different frequencies. Right? So this is what you see. The target is where target is where the collision takes place, but the filament is where the electrons are produced. So this is the hot filament. So the electrons are produced by thermionic emission. So they accelerate towards the target. This is the target. And the target is made out of dense material. And this dense material, right, will basically, when the electrons collide with this dense material, they will collide, and in this process, they will emit energy in the form of photons. Okay, let's try this example. Basically, to answer questions about X-rays and so on, right, we use the law of conservation for energy. So let's try this question. Pause this video. Okay, so let's discuss this question. An electron of energy, 3.06 times 10 negative 14 joules of energy, is incident on the target nucleus, right? It comes in with this amount of energy. So when it hits the target nucleus, then the electron is deflected with an energy of 6.08 times 10 negative 16 joules of energy. So the electron has lost energy. Okay, so in parting, right, draw an arrow to indicate the possible initial direction of the photon emitted. Ignore the recoil of the nucleus. So where do you think the photon, the X-ray photon, will be emitted, in which direction? And explain why. So the answer will be, it's going to be emitted in this direction. And the reason why it's in this direction, not any other direction, is because photons, right, are particles with energy and momentum. So in this case, right, the initial momentum of the electron, can you see, right, is along the horizontal direction. So therefore, the final momentum of the electron after it's deflected and the final momentum of the photon that's emitted, the resultant of these two momentum must be equals to the initial momentum that lies along the horizontal. So we visualize in the form of a vector diagram, the momentum of the electron and momentum of the photon. You can see that the resultant of these two vectors lies along the horizontal. Okay, B, calculate the energy of the photon. Calculate the energy of the deflected photon and the speed of the electron and the wavelength of the photon. Okay, to calculate the energy of the photon, deflected photon, right? Basically, we use the law of conservation of energy. So the law of conservation of energy states that the total initial energy, which is just made up of the initial kinetic energy of the electron, because the electron comes in with this amount of kinetic energy. The final energy, the total final energy, will be made up of the energy of the photon that's emitted here and the energy of the electron, because the electron still has a balance of 6.08 times 10 negative 16 joules of energy. So this is the final kinetic energy of the electron. So in this case, we can find the energy of photon, which is initial energy, kinetic energy minus kinetic energy final. So this will give us 2.99 times 10 negative 14 joules of energy. So this is equivalent to the energy of the photon that's being emitted. Okay, for part 2, right, what's the speed of the electron? How fast will this electron be moving? Since we have the energy, can we find how fast would it be moving? Yes, we can. We can equate to half mv squared. So since we know the energy, we can use this to find V. So V will be 3.86 times 10 to the power 7 meters per second. And C, what's the wavelength of the photon emitted? So energy, since we know the energy from part A, this is the energy of the photon, we can use energy to find the wavelength of the photon. So equating to this, we can find that the photon will be 6.55 times 10 negative 12 meters. So this will fall under the X-ray region. Okay, next, sketch a graph of the spectrum for an X-ray tube, showing the three main features of the spectrum. So the three main features, all right, of the spectrum, all right, produced in this way are continuous range of frequencies, is known as Bremsstrahlung radiation, the existence of certain maximum frequency of radiation, where Fmax equals to E delta V over H. Delta V is the tube potential, and high intensity peaks at particular frequencies. These are known as the characteristic lines of X-ray. So when we sketch the X-ray spectrum, right, we can see these three main features. Okay, so we have to explain what causes the three main features. So the continuous frequencies are this one. When I use tube potential V1, the tube potential will be the potential between the filament and the target, the high tension potential. So when I set V1, I will see a continuous range of X-ray frequencies that's being produced, right? So what causes this continuous range of frequencies? So this can be explained from the initial slide that I show you, right? Depending on how close the electron hits the target atom, all the electrons are losing energy. And the energy lost by the electron depends on how close the electron approaches the target. The closer they are towards the target, the higher energy of the photon that's being emitted. So since you have a range of basically a big multitude of electrons that's colliding with the target atom, you find that all the photons will be emitted with a range of energies. So a range of energy implies there must be a range of frequencies, all right? The next one will be maximum frequency. Okay, how do you account for this maximum frequency? So the maximum frequency will be when the electron hits the target in a head-on collision. So when it hits the electron in a head-on collision, then all the energy of the electron will be lost. Then just one collision. So therefore, a photon of high energy will be emitted with maximum frequency. Okay, the characteristics lines, right? These lines, right, is a property of the metal. So this will be explained later in subtopic 3.3, right, when we learn about structures of the atom. So explain the continuous range of frequencies. Like what I explained just now, why is there a continuous range of frequencies? And why there is a maximum frequency? Okay, so to explain the continuous frequency, it all depends on how close the electron approach or collides the target. The electron loses varying degree of kinetic energy. So depending on how close this electron approaches the target nucleus, so the closer the electron approaches the target nucleus, the higher the energy lost by the electron. So the energy lost by these electrons are converted to photons. Since there are a great number of electrons colliding simultaneously with the target nucleus, they would release photons with varying degree of energy, hence a continuous range of frequencies. Okay, explain the maximum frequency. So maximum frequency is produced when the electron makes a head-on collision or direct collision with the target nucleus. So when the electron loses all its energy in that just one collision, so hence a photon with maximum energy will be released. That means the photon has maximum frequency. Okay, derive maximum frequency and solve problems of maximum frequency. So how do you derive this? Again, we use the law of conservation of energy. That is total energy initial equals to total energy final. Okay, let's look at this. Total initial energy will be what's the energy of the electron at this position. So the electrons, right, has kinetic energy. And the kinetic energy of the electron comes from the work done to accelerate the electrons from the filament towards the target. And the work done is given as Q delta V. So delta V is your tube potential. So in other words, right, if I apply 100 kilovolts across the filament and the target, the electrons will gain 100 kilo electron volts of kinetic energy. If I apply 120 kilovolt potential, then the electrons will gain 120 kilo electron volts of potential energy when they hit the target. So this here represents the initial energy of the electrons. It all depends on the tube potential. Okay, the final energy depends on how the electron collides with the target. So the electron comes in with high energy, initial energy. When it hits the target, it might retain some of its energy. Like here, right? It comes in with high energy, it retains part of its energy. So there is kinetic energy final. And since it loses energy, the energy will be converted to photons. So the final energy is made of energy of photon plus kinetic energy final. Okay, so if we equate from law of conservation of energy, this is my initial energy of the electron that comes in equals to total final energy, that is energy of photon plus kinetic energy final. So in the case, right, where the electron comes in, like if you see, right, the electron comes in, and it hits the target in a head-on collision. That means the electron stops and it loses all its energy in just that one collision. So what happens is the photon will be emitted, where this photon will be of high energy, high frequency. So from the law of conservation of energy, if the electron stops, that means kinetic energy finally equals to zero. That means all the energy will just be of just one photon. So since this photon has all the energy, that means this photon will have maximum energy or maximum frequency. So therefore, from here we can find the maximum frequency is equal to E, the charge of electron, times the tube potential divided by Planck's constant. Okay, in this question, pause the video, and once you're ready, resume your recording. Okay, in this question, electron of energy 3.06 times 10 to the power negative 14 joules, incident on the target nucleus in a head-on collision. It comes in and collides onto the electron, onto the nucleus, right? So calculate the tube potential, what's the maximum frequency, and what's the momentum of this photon. Okay, to find the tube potential, again, we use the law of conservation of energy. That is, the kinetic energy of the electron equals to the work done, which is Q delta V. So in other words, we can find delta V, how much potential required to accelerate the electron to this amount of kinetic energy. So kinetic energy divided by charge of electron gives us 191 kilovolts. That means the tube potential between the filament and the target is at a 1.91 kilovolt potential. So B, what's the maximum frequency of X-ray photon? Okay, using the formula that we just derived, F max equals E delta V over H. So we know the tube potential is 191 kilovolts, we know the charge of electron, and we know Planck's constant. So we can find the maximum frequency of the photon to be 4.61 times 10 to the power 19 hertz. And C, what's the momentum of this photon? So momentum will be h over lambda. So you see our energy is given as hc over lambda. So momentum, right, is actually h over lambda. So I can write momentum is energy divided by c. So this is another way I can represent the momentum of a photon. Rather than using h over lambda, from the frequency, I find lambda. And once I find lambda, I find the momentum. I can do that. Or I can use this formula. Because energy is h over lambda. Or basically, momentum is energy divided by c. So I already know the energy. I just divide by c. So this will be the momentum of the photon. Okay, let's try this example. An X-ray tube has an exciting potential of 75 kilovolts. So what's the kinetic energy of the electron when it hit the target? What's the speed when it hit the target? What's the shortest wavelength X-ray that can be produced? And what's the wavelength of the photon emitted if the final speed is 3.10 times 10 to the power 7 meters per second? So pause this video. Okay, so let's discuss. So what's the kinetic energy of the electrons when they hit the target? So using the law of conservation of energy, the kinetic energy equals to the work done, Q delta V. So the electrons have charge E moving through a 75 kilovolt potential. They are going to gain 75 kilo electron volts of kinetic energy. So change it to joules. So 1.2 times 10 negative 14 joules of energy. B, what's the maximum speed of the electron when they hit the target? So since we know the kinetic energy, we can find how fast they'll be moving, which is equal to half mv squared. So equal to 1.2 times 10 negative 14 joules. So from here, we can find V to be 1.62 times 10 to the power 8 meters per second. Okay, always take note when you find the speed of electrons and so on, right? Always ask yourself, is it possible to be traveling at this speed? If as long as it is less than the speed of light, then yes, it's possible. So if you get something that's greater than the speed of light, it should highlight to you that something is not right. Most likely you did a wrong conversion from electron volts to joules. So double check, all right, you're working. It must always be less than the speed of light. Okay, see, what's the shortest wavelength X-ray that can be produced? Okay, using this formula, frequency max equals to E delta V over H. So we can find the frequency to find the shortest wavelength. Right, so we get this frequency. This is known as maximum frequency. So once we have the maximum frequency, we can find the shortest wavelength because lambda is C over F. If F is maximum, lambda will be minimum. So from here, we can find the shortest wavelength is 1.65 times 10 negative 11 meters. Okay, for D, right, what's the wavelength of the photon emitted if the final speed is 3.10 times 10 to the power 7? Okay, to explain this, again, using the law of conservation of energy, initial energy will be the kinetic energy of the electron, which is dependent on Q delta V or E delta V. Final energy will be dependent on the final kinetic energy plus the energy of photon that's being emitted. So in this case, the electron still has part of its kinetic energy, which is its final kinetic energy, because we know it is moving. So from here, we can find the frequency of the photon, which is the initial energy minus kinetic energy final. But what's kinetic energy final? We use half mv squared again, all right, to find kinetic energy, half mv squared, because it's moving at 3.10 times 10 to the power 7. Substitute into here, we can get the energy of a photon will be 4.38 times 10 negative 16 joules of energy. So initial energy is given as this, final energy given as this. So we can see how much has the electron lost during this collision. So it has actually lost 1.156 times 10 negative 14 joules of energy. And the energy lost by the electron will be converted to a photon. So from here, we can find the frequency of the photon. Once we have the frequency, we can find lambda. And solving this, we can find lambda to be 1.72 times 10 negative 11 meters. So when you get this, ask yourself, does this make sense? Yes, it does. Because the minimum lambda is 1.65 times 10 negative 11. So the lambda that I find must be larger than the minimum value. All right.